Hello, this is the BoF. I'm going to talk about optimizing copy function and what does it do with the RISC-V CPU core design and network speed. These are the topics I'm going to cover. Everything started when I received the BeagleV Starlight beta program board. I think that was end of March, and I started to dig in on May. And there was a discussion about improving network speed. Many people was joining at the forum and discussing. I wanted to help. So there's a two type of the copy function inside the kernel. Most of the copy function, it's used for small size of the copying inside the kernel. However, for the network usage, it uses large size. I'm going to talk it later. For example, 1500 bytes or 9,000 bytes. And what does the large size copy have to do with the RISC-V core? What's the difference between the historical copy function? And also, optimizing the copy function, it does help what you learned at the compute architecture book, a quantitative approach, which I learned from second edition. And I'm going to explain why it helps. And the rest is talking about my implementation and the patches, and also the people who was working together, Matteo and many other people. Okay. All the discussion today is pretty much similar with the Starlight board and Unmatched board because both uses Sci-Fi U74 Core. Today's slide is mostly based on the result from the Starlight board because it's smaller footprint on my disk. For me, it was easier to run it on my disk, but it should be pretty much the same between the Starlight and Unmatched board. And the right side is the result of the running the network bench iPerf3 and also running the perf-top, and two function was having a large CPU usage, memcopy and copy to user. And typically the board with 1 gigabit Ethernet tend to have 890 megabits per second speed maximum, and that's how it was achieved at the last. On the right side it says after 904 megabits per second, 898 megabits per second, but initially it was around 600 something. This time it was 686, 683, but yes. So it's a story from how we observe the root cause of the overhead with two functions and how to optimize it. Where to optimize in the copy function. U74 Core, it has a load and store instruction to access the main memory, and 8-byte 64-bit boundary memory access, it performs very well. I mean, because it's aligned address and it's supported with the U74 Core. However, unaligned address for U74 is 1-byte boundary, 2-byte boundary, 4-byte boundary. It's not implemented, so it's trapped as an illegal instruction set, and it's handled inside OpenSBI. And so two things happens. One, memory access, which is not aligned with the 8-byte address, will generate legal instruction trap, and then switching from kernel mode and S mode, from M mode and OpenSBI for every instruction, and switching back. That's one observation. And another point was the size of the copying data. Typically inside the kernel, it doesn't use large size for copying. Mostly the memcopy or memset or memmove or use less than 64-byte copies. However, for the network application, first application written on the user space will use the send or receive typically with the socket API, or you could use read and write, but typically from the Unix historical network program will tend to use socket API. And passing the data through the API, instead of passing 1 byte each, typically people will write allocating large buffer in the user space and pass it to the kernel with one system call. In this example, the left side is a 1 byte copy, the for loop, and the right side is 1500 byte and one system call. On the right side is faster because it has less switching between the user space and kernel space. Context switches has an overhead on CPU. It may not show up well on emulator or QEMU, but if you're really running on the real hardware, it does show up the overhead. Memcopy and the copy to user function inside in this kind of usage is tend to have a large size of copying, because network byte has a maximum transmit unit called MTU. It's 1500 bytes for most of the usage. However, that 1500 byte is getting smaller for supporting gigabit over, like 2.5 gigabit. So many network switching hub started to support jumbo frame, which is 9000 bytes. The buffer size used on network application keep going to get larger. It's not going to go back to smaller size. And this is the place where the CPU design has an impact on copy function. Typically known, the loop unrolling will improve the performance, but at the same time with the cost of increasing the binary size. However, it's really well known unrolling is going to help, because U74 is in order 5 to 6 pipeline stage, and single issue 5 to 6 pipeline stage is going to have read after write data hazard if you do not loop the unrolling. Most of the time, compiler is meant to be responsible optimizing, but in the copy function, compiler does not have much option to optimize it. So manually handwriting make the program friendly for the in-order CPU core. The word of the read after write data hazard is come from computer architecture, but the one I learned is the second edition, Quantitative Approach. My old one, it's brown and it has many post-it to good to reference. And the chart from the book is pretty much the same with the implementation of the U74. It's not much different. The condition described in the computer architecture book pretty much the same applies how to optimize the copy function with the loop unrolling. Learning from good architecture book from the good author does play a big role. For improving the performance, both type of the copy function was required to improve it. So Matteo was optimizing regular copy function used inside the kernel, memcopy, memmove, memset, etc. These are the copy function automatically inside the kernel. When the page fault is occurred, the Linux kernel inside will automatically allocate the page and then come back to function. So do not have the special handling inside the copy function. So you could write it completely in C. Before Matteo optimized it, it was written in assembler. So it was making more generic. Writing in C will make it to use compiler wisdom. It's good to write many portions as possible in C. The portion I optimized was copying function between the kernel space and user space. For example, network application will send the data from the user space to kernel. When the kernel receives the data packet from the network devices, it will pass the data to the user application. It's the same with when you write the program with read and write on the file system. It will hand over going through the kernel space and user space. So the function it's used was copy to user is from the data copying from kernel space to user space, and copy from user is the copying from user space to kernel space. And in this function, it won't automatically handle the page fault, so it needs adding the manually handling page fault. Typically, it's written with a mix in C and assembler, and I would like to make it in combination with C and assembler in the future, but right now I rewrote in assembler because it was the initial function were written in assembler, so it was less overhead for me. And this portion was merged in kernel 5.14, and Matteo also have sent his patches on few times on mailing list and not merged yet. So what we're going to do is going to talk at the last page. This is the source code, putting all the discussion in one place. The one I optimized in copy to user and copy from user. The link is the where it's located. It's underneath arc/risc-v/lib/uaccess.s. So it's assembler source code. So it starts from the left side. The copy function will check the source and destination address, whether it is aligned for 64-bit CPU. If it's not aligned with 8-byte boundary, then it will copy until only the destination address is aligned, because not always possible to make the both source and destination align in 8-byte boundary. So coincidentally, if both source and destination address could be aligned or will be aligned in 8-byte, then on the most of the right side function is going to be used. It's using word copy. Each iteration, each load and store is done with 8-byte. So both source and DOS are aligned. So operating copy in loop unrolling. So it's unrolled 1, 2, 3, 4, 5, 6, 7, 8. 8 unrolled copy function. Consequent and load, keep loading before store, because loading and store next to next back to back will cause the in order pipeline stall with the read after write data hazard. So load many as possible and then store many as possible. And the middle one is the little tricky part, which is I rewrote from scratch based on the Gary's copy function. So Gary also have submitted the patch in the past, but it wasn't accepted, and I was fixing with the not over yeah, anyway, I was fixing not to overwrite or over access the area of the source and destination. So what really does is if the destination is aligned to the 8-byte boundary but source is not, then you read the source address in the 8-byte boundary, but it will have when you read it in the register, the location is a bit shifting, so shift it manually and then fix the fix the data with the shifting and then write it back to the destination. Which was a little bit tricky to read, but if you understand, going through the code, I try to write as much of the comment inside the code, so I hope it will be able to understand. Matteo's is doing the same. Matteo's mem copy is doing the same in C. So these are the notes from my notes when I was implementing the shift copy. Yeah, RV32 must be aligned with a 4-byte boundary, and RV64 for U74 is a 8-byte boundary. So the copy function must be work on both CPUs. So writing down the address and writing down the data and how many shifting is it meant to be fixing before they write it back. And these are some of the notes. So this is the good part. Result after applying the patches. So the left side is CPU usage. In the beginning, copy to user used to consume like more over 30% of the CPU usage. After applying the patches, 33 on the left side for TCP receive reduced to 13.76%. TCP send was 9.84% to 7.337%, which is not that much, but still, and the UDP send was from 22.50% to 9.49%, and the UDP receive was 31.04% to 11.22%. And the right side is the bandwidth changes. This is included with the Matteo's memcopy improvement patches. So initially the maximum bandwidth was 680 something ish megabits per second on gigabit Ethernet, which is not the maximum of the hardware. So after the patches, definitely maxing out the hardware capacity, 898 megabits or 904 megabits per second. Really good. Yes, this is the main reason I applied for this talk as a BoF, because I wanted to attend to the RISC-V summit in person and meet all the people, for particularly RISC-V Linux maintainer Palmer and other major contributor Drew and the maintainer of Perf and etc. Yes, so then we could have interactive discussion at the same time, and we could go home with what to do for the next as a homework. Yeah, but I'm sorry, I'm stuck in Japan. So I will look for the next time. And we really would like to have Matteo's patches to be in the main kernel. I mean, in the upstream kernel, because majority of the copy is done with the memcopy, and also for the my portion, as I slightly mentioned in the few pages before, is would like to convert fully written in assembler to partially converted to C source code with partially written assembler, which is trapping the page fault in assembler is the only portion must be written in assembler. So that's what I would like to do in the future, but haven't done it because just don't have the time right now. And one of the reason Matteo's patches is so another thing what we need to consider for the optimizing function, for example, copy function, which is inside the kernel, there's only few places it could dramatically change the performance of the kernel with like 2 or 3 function optimization. The copy function is probably the only places to do that. Other places in the kernel and trying to improve the performance, it requires many tiny optimization, but copy function is dramatically could have an impact. So it's very important to have optimized copy function. And historical embedded engineer will rebuild the binary only for the targeted CPU, so they do not care of the other CPU design. However, if you going through the slide, it's the optimized copy function tend to differ with the CPU design. If it's in order core, in how many pipeline stages. If the pipeline stage is longer and the in order single issue core, pipeline core, then the loop unroll must be more larger, like old days in MIPS. And if it's out of the order core, then if the out of order inside the CPU core is well implemented, then may not have to do the loop unrolling. It will be great because loop unrolling is going to will increase the binary size. So if the out of the order core is able to reorder by themselves inside the CPU core, then the optimized function core, optimized copy core, could be not having the unrolled loop unrolled. So it's all depends on the CPU design. However, Linux kernel historically would like to have a single binary kernel for the one CPU architecture. For example, on Intel, AMD, Intel all has a different design, and also even an Intel core, it every 2 years comes out with a different design, and optimized copy function is slightly different. So it's yeah, Linux kernel tend to prefer choosing the best function on runtime. So yeah, if we how to we to um, make it make the same situation like Intel on Linux kernel on RISC-V, or making a similar x80 x64 sorry, making the similar uh, making the similar activity done on x64 on RISC-V. Yes, we need to consider how to achieve it. And also all this activity on my side was I was doing everything in my spare time from March, no, mostly from May. So if to go through on this one, go persuade on this activity, I need to finish my other job on TEEP as soon as possible so I could allocate more time on this. But yeah, let's see. And this is the procedure how I took the benchmark result. So if you would like to reproduce the result, change the IP address in this slide, then you could yeah, reproduce and if you could help the revising the patches, it will be great. So I think that's it for my slide. So we'd like to have many Q&A session. Probably what's going to be on the Zoom with the text chat, but thank you. Hello. Yeah, is my voice okay? Yeah. Okay. I have a question. How's the performance on x86, Intel x86? So that's something we measured the first, and x86 had about the performance around 890 to 90 megabits per second, as we as it was shown in my slide after applying all the patch from Mateos and me. So yeah, so it's yeah, Intel's CPU typically is doing well, and we wanted to have the similar result on RISC-V, and I think we are achieving pretty much the same result now. But yes, and also the question is about yeah, difference between Intel and Intel x86 and RISC-V unaligned memory access. Yeah, Intel is very good on optimize inside the hardware for the unaligned memory access. Intel's x86 is 64-bit CPU, so typically it will expect 64-bit bit boundary, which is 8 byte, will be the fastest, and the other boundary will be slower. If you try it with by yourself with many writing assembler, it's really good. x86 really good at handling unaligned memory access, almost no penalty, as if. So they are doing very good, probably doing with a longer prefetch and many good stuff inside with more transistor in it. So yeah, so that's x86 is meant to do well from the old binary, which started from 386, which didn't have to care much about online access or unaligned access. So, however, most of the RISC CPU like MIPS and RISC-V and even ARM and PowerPC, if the aligned access or unaligned access does play a big role. Yes. Mm-hmm. Yeah. I hope it's a good. It's a morning in Japan. I hope it's a good time in other time zone. Yeah. I see. 5, I see. 4:30 for yeah at the conference. Uh, I really wanted to visit San Francisco. San Jose? Yeah, San Jose. Oh, the question is typical memory size depend. I mean, it it really depends on the user space application. For example, if you're reading the programmer for the reading storage would like to use a large buffer size as possible. The network, if you make the buffer size larger than MTU size, then the kernel, it will make a fragmentation in the packet to send from the kernel to the Ethernet. So typically the programmer will optimize their packet size based on the MTU size. So yes, so it depends, but most of it depends on how the programmer really care about the performance and try to maximize the size with the closest as the MTU size. And MTU size is regular MTU size 1500, and jumbo frame is depends, but typically it's from 8,000 to 9,000. Yeah, out of the order core for the suggestion for the. Do you have any suggestion for the RISC-V out of order core? It depends. Well, we'd like to talk about how the detail how to optimize an out of the order core from the hardware designer, but typically it have the copy function require less consideration of the unrolling for the out of the order core, because the hardware should be responsible of reordering the preventing read after write hazard and other data hazard. So yeah. Well, typically it will make easier for the programmer and reduce the binary size. Okay. I really want to see out of order core coming out on RISC-V, because this is my experience. In order core, out of the order core, if you run the benchmark, it perform in order core pretty much good as out of order core most of the time. However, if you using regular application on Linux terminal or something, out of order core feels more faster. it feels more interactive with a low latency than the result of the number on the benchmark. So yeah, I'm looking really forward with the RISC-V coming out with out of order core. Thank you. Seems like that's all. No, thank you for taking your time and listening to my talk, and happy to have work together optimizing the Linux kernel on the RISC-V. Thank you.